Next, let's review instantaneous velocity. So remember that instantaneous velocity is the slope of the tangent line to, again, a position time graph. So a tangent line touches our curve at just one point. So that's a tangent line at, let's see, that's about maybe 3.8. Tangent line at 1 here, maybe look like that. Right? So our instantaneous velocity is our slope of the tangent line. And let's see, what do we know about the slope of the tangent line? That is our derivative. And hopefully you recall the definition of the derivative. It's the limit as h goes to 0 of f of a plus h minus f of a over h. And remember that our h is a distance, so if we have a point A down here, then this would be a plus h if this distance right here is h. So our h has units. Let's write this out with units. So h is a distance in seconds. And f of a plus h is the y value that matches up over here. So f of a plus h has units in meters. And then f of a is the y value at a. So minus f of a, and f of a, since that's a y value, is meters. So we're going to get a value that is in meters per second. So again, we're getting units that match up with velocity. Luckily, we know shortcuts about derivatives now, so we don't have to use the definition every time, and that'll be helpful as we find our instantaneous velocities. Let's answer some questions involving instantaneous velocity now. So here we have some questions about instantaneous velocity. So our first question is, at what time or times is the instantaneous velocity greatest as the car moves west? Now remember that we said that the car moved east first. We moved east first, and then we started moving back west right here when our position started getting closer to our starting point again. So we're looking between here and here. When is the instantaneous velocity greatest? So remember, instantaneous velocity, that is the same as the slope of the tangent line. So we're really asking, when is the slope of the tangent line greatest, or the steepest? So let's see. If we were drawing lines, we'd have a line here, 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 and here, here. So it looks like right around here, maybe around time equals 2, we would have the greatest instantaneous velocity as the car moves west. All right, next question. At what time or times is this speed the greatest? So first we need to talk about the difference between velocity and speed. So velocity is the derivative at time t, okay? So, and that can be negative or positive. Can be negative or positive. See, we had positive velocity, positive slope, then negative slope, then positive slope. So our velocity was positive, then negative, then positive. But speed, on the other hand, is the magnitude of the velocity. So what that means is that we don't care in what direction. We don't care if it's negative or positive. It's always just positive. So speed is the absolute value of the velocity. So it's the absolute value of the derivative. All right, so our question is, at what time or times is the speed the greatest? All right, so what this question is asking is, where is the tangent line? Where is it most vertical? So where does it look most like a line going up and down? All right, so if we were to draw some of these tangent lines, so what do you think? Where do we look most vertical? Well, it looks like our lines look most straight up and down at the beginning and towards the end of our position. So it looks like our speed is going to be the greatest at time equals 0 and time equals 4 seconds. So at what time or times is the car stopped? So we know that if a car is stopped, it's not going anywhere, so we have no velocity. And velocity is, or instantaneous velocity is the same as the derivative, which is the same as the slope of the tangent line. So we're looking for when the slope of the tangent line is 0. And if we have no slope, then we have a horizontal tangent. All right, so where do we have horizontal tangents? There and there. So at time equals about 1.1 and time equals 3. So now let's say that we're given the position function again up here, and we're asked to find the velocity function. So remember, the velocity is the instantaneous velocity is the derivative. So we need to take this derivative. So the derivative is the same as the velocity. So using our shortcuts, we get 3t squared minus 6 times 2t plus 9. So that is 3t squared minus 12t plus 9. So let's say then we're asked to determine the velocity at time equals 1. So we have a velocity function. So our velocity is equal to 3t squared minus 12t plus 9. And we want time equals 1. So everywhere we see a t, we're going to plug in 1. So v of 1 equals 3 times 1 squared minus 12 times 1 plus 9. So we get 3 minus 12 plus 9. So it looks like that is 0. So the velocity at time t equals 1 is 0. And remember, we're in seconds and meters. So this is meters per second. All right, now let's talk about the second derivative. What do you think the second derivative will tell us? Well, let's see. So we start off with a position versus time function. And when we took the derivative, so if this was, this was s of t, our position function, then our derivative gave us a velocity. So now we're going to graph that new s prime of t, which was our velocity, on the y-axis. And our x-axis doesn't change. So this was our s of t. But now if we graph the derivative with respect to time. So before we had our change in y over change in x was our change in position over our change in time, and we got meters per second. So now if we do change in y over change in x, we get change in velocity over change in time. Our velocity units are meters per second. Time is still in seconds. So we get meters per second squared. And do you recognize those units? Hopefully you recognize them as units for acceleration. So acceleration as the rate at which the velocity is changing with respect to time. And acceleration you can think of as stepping on your gas pedal in your car. So here, if we look at this graph, we have a negative slope over here, so negative acceleration. So that's like braking. And then over here, we have positive acceleration, so they're stepping on their gas pedal. So here they had a pretty constant stepping, slowing down, slowing down, slowing down, slowing down. Here is a gradual acceleration, 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 acceleration. Alright, so we know our second derivative is acceleration. So if we're asked to find the acceleration and we're given a function, alright, so we need to find first we need to find the first derivative. So that will give us the velocity. And we found that it's 3t squared minus 12t plus 9. So now for acceleration, we need to find the second derivative. Gives us acceleration. So we get 6t minus 12. Alright, and then we're asked to determine the acceleration at time equals 1. So everywhere we see a t, we're going to plug in 1. The acceleration at time equals 1 is 6 times 1 minus 12, which is negative 6. And we're in meters per second squared.